become very important in our school curriculums. It's a difficult subject in school because we have to learn a lot in a small amount of time. Exams are very competitive. We all want to get into the best colleges and so on. And so somehow learning mathematics has become a very stressful activity. And I hope that today we don't, I want you to forget about all that. Just we'll have 3 lectures today. I'll be giving the first one on integer sequences. The second one will be by Professor Balasubramaniam, who used to be the director of this institute until very recently. One of the very prominent scientists here. He'll be talking about cryptography, or rather number theory and the art of sharing secrets. In the afternoon, we have a talk which is not strictly mathematics. It's on gravitational waves, which was a sensational discovery in astronomy not so long ago. Okay, so that brings me to I'll tell you a little bit about the Institute of Mathematical Sciences. So this institute is 54 years old. Am I right? Yeah. And it's based in the verdant surroundings of the CIT campus. I don't know if that's still true anymore, but it's an institute where we do mainly theoretical research. We don't have any labs. We don't have any experimental setup. We have 3 groups. We have the biggest group here is actually a group in theoretical physics. So and then there's a group in mathematics, and there's a group in theoretical computer science. We would have said theoretical mathematics, except mathematics is generally theoretical. But today I'm going to talk a little bit later about experimental mathematics. So we have mainly PhD programs. So that's our focus. We do research and we train people to be scientists. And the PhD program is something you can apply for after doing an MSc, or we have an integrated PhD program which you can apply for after doing BSc. So, so we have these 2 programs basically. So for all of you, this is still probably far away if you're interested. It's good to know a little bit about what we do. So, so as I was saying, when I tell people that I'm a mathematician, I get this sort of either they kind of, mostly some people are okay with it, but most people sort of freak out and they don't want to talk to me, and then they're a little scared of me, and they think I'm going to give them problems to solve next, or maybe integrals to do or something. But also I think part of it is it's difficult to explain what it is on a day-to-day basis that mathematicians like me do. So what do mathematicians do? There's a famous quote by the mathematician Paul Erdős, who said that a mathematician is a machine that converts coffee into theorems. So basically we drink a lot of coffee and we prove theorems. That's our job is to formulate and prove theorems in some sense. But that still doesn't explain what it is we do. How do you decide what theorem to prove today? Do I come to my office and then my boss gives me a list of theorems and then I try to prove it? Maybe he gives me a bunch of integrals and I have to solve them. So how is it that we work? So in some sense, in practice, mathematics is not so different from the other sciences. We are basically curious people. There are a lot of questions out there about so scientists usually look at the world around us, the physical world around us, and they are curious about it. They want to understand it better, and they conduct experiments. They draw from their experience. They also learn from scientists who have worked before, and then they try to advance their understanding of the physical world. So for us, in mathematics there is also a mathematical world out there. So these are things like numbers. We'll talk about prime numbers a little later today. These are constructions which, strictly speaking, are in our minds, right? You won't, I mean, but to us they're just as real as, say, the moon out there in the sky, the prime numbers, and we are curious about these things. Some of these problems are very, very old. So many of the problems that mathematicians work on today are have their origins, you know, in sometimes hundreds of years, sometimes thousands of years. So, and then of course mathematics is largely a social activity. We respond to what other people are doing across the whole world. So there's a lot of it's not something that you know, one culture does. It's a very, I'll talk a little bit about this later in my talk, about how mathematical ideas travel across the whole world. Okay. So let me now get to my presentation as such. So I'm going to talk about integer sequences. So now my son is in class 4 and he likes these math puzzle books, and they have things like this. Can you guess the next number? 25. How do you guess that? These are the square numbers. So these are all the perfect squares. Okay, that. So you have even a formula for them. An is n squared. N taken n times. Oops, what did I do? Okay. So, oops, yeah. Why are they called square numbers? Because they count the number of points in square arrays, right? So here's a 1 by 1 square array. It has 1 point. Here's a 2 by 2 square array. It has 4 points. Here's a 3 by 3 square array. It has 9 points, and so on. Now here, I've sort of drawn the arrays nested inside each other, and this will give us an idea of how these numbers grow. So the difference between 25 and 16 is just these two edges of squares. How many squares are in here? 9? 2, 3, 4, 1, 2, 3, 4, and 1. 2 times 4 plus 1, that's 9. And we need this off. Yeah. And oops, and how many are here? 7, right? So 2 times 3 plus 1, and here it's 2 times 2 plus 1, and here it's 2 times 1 plus 1, and here, well, 2 times 0 plus 1. So the difference between these numbers are odd numbers. And so here we've made another discovery about this sequence. These square numbers are also the sums of the first n odd numbers. So that's square numbers, a nice easy sequence to start off with. Now this brings me to the story of triangular numbers. So I don't know how many of you have heard this story. There's this German mathematician Carl Friedrich Gauss, and Gauss, like for us he's like a big deal, you know, one of the greatest, smartest people who ever lived. So when he was 7 years old or something, his teacher gave him this problem. All these kids were, you know, annoying the teacher, and the teacher wanted to shut them up for some time. And the teacher said, okay, here's your problem. Add up 1 plus 2 plus 3 plus 4 all the way up to 100 while I take a nap. And he just, you know, took off his shoes and put his feet up on the desk and was about to fall asleep when Gauss said, Sir, the answer is 5050. And what's the next number here? 20? 2, 1. I already sort of gave you a hint as to what these numbers should be with my story. These are the triangular numbers. So if you know what square numbers are, you can imagine. But here's one way of thinking about that, is the sum of the first n integers. So what the problem that Gauss's teacher gave him was that find the 100th triangular number in some sense. Okay, so how do you think Gauss solved this problem? Well, it's not documented in history how he did it, but people suspect it was something along these lines. It's a clever little trick to solve these problems. So you want to add up the numbers 1 plus 2 plus 3 all the way up to 100. So we just have to do it once, but let's do it twice. But the second time we'll add them up in reverse order. So the second time we'll write 100 plus 99 plus 98 all the way up to 1. Okay, but you know that if you add numbers, the order in which you add them doesn't really matter at all, right? 2 plus 3 plus 5 is the same as 5 plus 3 plus 2. And so also with 200 numbers, I can add them up in any order I like. So let me just add 1 plus 100. That's 101, right? And 2 plus 99 and 3 plus 98. See, every time you move to the next column here, the number on the first row goes up by 1 and the number in the second row goes down by 1. So their sum remains the same. It's always going to be 101. So you get 101 plus 101 plus 101. How many times? 100 times. So 2 times the sum which we want to compute is 101 times 100. So the sum we want to compute is half of that, which is 5050, which is one possible way that Gauss may have done this. Okay. So what's the next number here? 21. Last time also you said 21. Huh? So what are these numbers? So this is again a very famous sequence for those of you who keep track of sequences. It's called the sequence of Fibonacci numbers. So Fibonacci, if you want to formally define it, you say, okay, the first number of the sequence is 0, A0 is 0. The second number of the sequence, A1, is 1. And each number in the sequence is the sum of the two previous numbers. So this 1 is 1 plus 0. This 2 is 1 plus 1. This 3 is 2 plus 1. This 5 is 3 plus 2. 8 is 5 plus 3. 13 is 8 plus 5. And therefore, the next number is 13 plus 8. So it's 21. And after that, you'll have 21 plus 13, which is 44. 34? Okay, 34. It has an amazing formula. This formula is due to De Moivre, and if you were to look at this kind of an expression, you would never imagine that 1 plus root 5 by 2 is a horrible number. It's not rational. Yeah, it's called the golden ratio, so maybe it's not that horrible, but I don't know, at first sight it looks terrible. It's not a rational number, and then I'm going to raise it to n, then I'm going to take another horrible number, and then I'm going to raise that to n, and then I'm going to take the difference, I'm going to divide it by another horrible number. How would I possibly get integers? But it turns out that this formula does work. So in this case, this sequence also, there's a nice closed formula for the nth term. Okay, I don't know if you've seen how to derive this formula ever. Google it, it's fun. Okay, this number is called the golden ratio, and it's supposed to have like lots of magical properties. There was a book sometime back called the Da Vinci Code, where this series and this number played a prominent role. It's supposed to be the most pleasing proportion when you have a square. It's supposed to be like, if you draw a spiral with this kind of growth, then it's supposed to be very beautiful. And they say that seashells form this kind of spirals, but actually when people looked at it, that wasn't true. So, so there are a lot of mystical meanings attached to these things. Some of them are true, some of them are just results of over imaginative minds. But it certainly plays an important role over here, and this number is sort of the conjugate of the golden ratio. So what are these? Actually, the best way to remember this is you have this equation x squared. So these are the roots of a quadratic equation, x squared plus x minus x squared plus x plus 1 or minus 1, I forget. X squared minus x plus 1? No. Okay, you work it out. So there's a quadratic equation for which these two are the roots. So the sum of the roots is 1 and the product of the roots is minus, so this plus this times this, right? So that's anyway. So find the quadratic equation for which these are the roots. You can easily see that if you take very large values of n, this thing more or less grows like the golden nth power of the golden ratio divided by root 5. Okay, so if you take n equals a very large number, you compute both these sides, they'll be very close. Okay, the ratio of the left side and the right side will have a limit equal to 1 if you want a precise statement. So this Fibonacci sequence, it's a lot of fun, and there's all these theories about it, but it's also actually really quite useful. So it has something to do with algorithm for finding the GCD of two numbers. So GCD, HCF, what do you call it? When I was in school, we called it HCF. GCD, greatest common divisor or highest common factor. Call it what you will. You know how to do it. So you have two numbers. Let's say we want to find the GCD of 21 and 13. Okay, remember those are prime. Yeah, no, 21 is not prime. They are Fibonacci numbers. So they are two consecutive Fibonacci numbers. Okay, so how do you find? Suppose I want to find the GCD of 4 and 6. What do? I take 6. I see how many times 4 goes into 6. Well, it goes in only once. The remainder is 2. And it turns out that the GCD of 4 and 6 is going to be the same as the remainder of 4 and 2. Okay, so the general principle is if you have two numbers a and b, say b is smaller than a, then you divide a by b and find the remainder. Then the GCD of a and b, let's say the remainder is called r, then the GCD of a and b is the same as the GCD of the b and r. Right? I think you've seen this in school somewhere. 9th? So you've forgotten. No, okay. So the GCD of A and B is the same as the GCD of B and R, but we know that R is strictly smaller than B. So this is good because now we have taken our old problem and made it a new problem which is smaller. And we keep doing this. Eventually what will happen is that the remainder will be 0, and that point, that last B that we get will be the GCD. So here I have tried to work out the GCD of 21 and 13. So when you divide 21 by 13, the quotient is 1 and the remainder is 8. And when you divide 13 by 8, the quotient is 1 and the remainder is 5. When you divide 8 by 5, the quotient is 1 and the remainder is 3. When you divide 5 by 3, the quotient is 1 and the remainder is 2. And this goes on all the way till you get 1. So what do we learn from this? We learn that the GCD of 13 and 21 is 1. We also learned that it took us an awful lot of time to compute the GCD of these very small numbers. Usually it doesn't take so many steps. In fact, the thing is, what do you notice about these things here? These are the Fibonacci numbers, and this here, oh sorry, maybe I should have written 2 times, 1 time, yeah, it's okay. So and these factors are always 1. So in some sense what we are trying to do, what we have here is the worst case scenario for the GCD algorithm. Because every time the number is going in only once, so it's growing, is the smallest number, the pair of numbers for which you need so many steps are 21 and 13. Okay, so if you're given any two numbers less than or equal to 21, it will take fewer steps. That's a fact. Okay. So the GCD of the nth and n plus first Fibonacci number will always take you roughly n steps, and this is the worst case scenario. If you have a number which is less than or equal to the nth Fibonacci number, or we have two numbers which are less than or equal to the nth Fibonacci number, the GCD algorithm will always take you at most n steps. Okay, so this is a worst case scenario, and so so what this says is that, okay, if I have two numbers, it gives me an upper bound on how many steps it takes for the GCD algorithm to run, right. So if I give you like two numbers, say if I give you 45 and something else, 45 and 33 or something. So then what you do is you find the first Fibonacci number that is greater than or equal to 45. So that's probably anyway 40, we saw 30 what? Okay, and so that's like maybe the 8th Fibonacci number or something like that. So the GCD algorithm should never take more than 8 steps. It's a guarantee. And these kind of guarantees are very important in practice. So anyways, so we saw that Fibonacci numbers grow fast. They grow like 1 plus root 5 by 2, which is roughly 1.766, 1.6 to the power n. This is anyway exponential growth, right. If you take 1.6, 1.6 squared, 1.6 cubed, it's an exponential growth. It grows very fast, and so Fibonacci numbers grow very fast, but so this means that the number of steps required to find the GCD of two numbers is very small relative to the size of those numbers, right. So this is a good thing for students who are getting GCD problems. It's a bad thing for teachers who want to keep them busy, but it's also a good thing for secure communications, because one of the key steps in the RSA public key crypto system, this is what we sometimes use for secure communications, like when you're buying something on Flipkart or Amazon, and then you want to make sure that the payment you make by your credit card is not observed by a third party. It's based on these kind of algorithms, and this ensures that this algorithm works fast in real time, that your computer doesn't just hang there because it's trying to find the GCD of two numbers and it's going to take too many steps. Okay, so let me just go a little bit into the history of Fibonacci numbers. So there's this thing, no scientific discovery is named after its original discoverer. This is known as Stigler's law of eponymy. Okay. So can you guess who discovered this? It was certainly not Stigler. It was discovered by Robert K. Merton. There's no space. Yeah. So it's the same thing with Fibonacci numbers. They were certainly not discovered by Fibonacci. So Fibonacci, who was Fibonacci? Fibonacci's real name was Leonardo Pisano, He was from this Bonacci family in Pisa, which was a city-state in Italy. So, in Italy, it wasn't a country. This is like we're talking about the 13th century. It wasn't one country. There were many city-states, like and Pisa was one of them. And there was a prominent family there called the Bonacci family, and Fibonacci means son of the Bonacci family. So, his name was Leonardo, and he was from Pisa, so he was called Leonardo Pisano. And this is an interesting part of the story. His father worked for the administration of this city-state Pisa. And his father was posted in a town called Bougia. It's now in Algeria, which is in the northern part of Africa. If you look at the map, it's not very far from Italy across the Mediterranean Sea. And it was there that he learned a lot of interesting mathematics. You know this decimal number system which we use, right? When we write numbers in digits, that system of decimals was discovered where? Here in Chennai? Somewhere in India. So, it was the decimals number system was actually discovered in India, and from India, India we had trading with the West, and these Persian and Arab traders, they took it to the Middle East and to North Africa. And Europe before the Renaissance was a country where there wasn't much science or mathematics happening, and Leonardo was lucky to be in Algeria at that time, and he learned the decimal number system from the scholars and traders in Algeria. And he introduced this decimal number system to Europe. He wrote a book called Liber Abaci, which means the book of calculation. This book, it's basically a manual to help traders, businessmen, to keep their accounts. So, it has a lot of algorithms for adding numbers, multiplying numbers. You've seen Roman numbers, like 15 will be XV and 200 will be XX. It's very difficult to add them or multiply them. Okay, but with decimal numbers, when you're in 4th standard or 5th standard or maybe even before, you learn these algorithms for multiplying them and adding them using carryover and whatnot, right? So, these ideas were introduced to Europe through this book. We're talking about the 1200s, so maybe about 800 years ago, they were introduced to Europe. This book didn't attract much attention at the time it was written, but it's proven to be very influential. Now, in this book, he had some weird kind of problem about rabbits. Okay, so this farmer, he starts with 2 rabbits, and then in 1 month those rabbits grow up and they give birth to 2 more rabbits, and after that every month they give birth to 2 more rabbits, and when the rabbits are born they take 1 month to grow up, and then after that every month they give birth to 2 more rabbits. So, like he starts off with 2 rabbits, and then the next month they grow up and they give birth to 2 more rabbits, and these 2 rabbits of course are still there. Now, these rabbits, they have to grow up, but these rabbits this month again give birth to 2 more rabbits, and these rabbits grow up, and then the next these rabbits give birth to 2 more rabbits, these rabbits grow up, these give birth to 2 more rabbits, and so on. And if you try to work out how many rabbits the farmer has, no rabbit dies in this farmer's farm, then it turns out to be a Fibonacci number. It's a bizarre problem, it's very contrived, it's frankly it's kind of weird. So, But the more important thing about this book was introducing the decimal number system to Europe. So here you can see a page from this book. It's written in Latin, but you can clearly see here the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. And look at the beautiful calligraphy. I mean, books had to be handwritten. There were no printing presses, and then they had to be copied out by hand. So this was the Liber Abaci. It's somehow he's most famous for this weird rabbit problem, but he also had this other important contribution. Here's another page from the Liber Abaci, and here are in fact the Fibonacci numbers 1, 2, 3, 5, 8, 11, 21. I guess this must be, yeah, what, 8? Yeah, whatever. So those are the Fibonacci numbers over there. But actually this, these ideas also go back to India. So in, there was a mathematician called Virahanka who lived in India in the 6th century, so nearly 600 years before Fibonacci in Europe. And you can see he was a very handsome man and he had a bird. So these people were interested in shlokas. So you have a shloka, and in a shloka you have short letters and long letters. Like in Tamil we have I. So is short, A is long, I is short, E is long. This is a thing which we have in Indian languages. It's not so clear in English. In fact, when we speak English, we completely make a mess of this. But English, you sort of stress one syllable in a word, but it's different in different words. But in Sanskrit, in Tamil, in most Indian languages, it's very clear that a syllable is either long or short, right? So you say Amma, it is is short, A is long. And when you write a shloka, what you want is, so there will be two lines, they must both have a fixed same length. And in this, when you count this, is 1 beat, A is 2 beats. Okay, so Amma is 3 beats. That is 1, A is 2. Okay, so we'll write that as 1 and 2. 1 means short beat, 2 means long beat. So is 1, A is 2. E is 1, E is 2. Okay. So now what we want to do is, we want to write a line of shloka. Instead of writing the actual words in Sanskrit or Tamil or whatever, we will write only whether it is long or short. Okay. So you write 1, 2, 1, 2, 1, 2 and so on. And so you want to know the total length will be just adding all the 1s and 2s. So Amma, the total length is 3, right? And so let's see, if you want a line with 1 beat, you can only have a short syllable, nothing else is possible. If you want 2 beats, you can have 2 shorts or you can have 1 long. 3 beats, here is Amma, 1, 2, okay, 1 short and 1 long, but you could also have something with 1 long and 1 short. Give me an example. Ama is too long. Adu is 1 long and 1 short, right? And what about this? Paravai, I is long, I think. Maram, very good. Actually, Maram is too short because that's im. Kadagu. Kanavu. Okay, that's good. So that's 1, 1, 1. Okay, and we are only interested in how it sounds. We are not interested in the meaning or anything. We are only interested in how it sounds to the ear. And so these guys, they were interested in this, and they tried to count how many different combinations you can get. So in terms of mathematics, what you're saying is you have to write some 1s and 2s. Total should be 4 or 5 or whatever, we'll say n, some number n, and how many different ways can you do it? Okay, so that's the mathematical problem. So, but if you want, so let's just look at this. So, so suppose I want to know how many patterns I can get with 4 beats. There are 2 ways of doing it. I can start with a pattern with 3 beats and add a 1 to this. So, I'll take 1 1 1 1. Okay, that's this one. 1 2 1 and 2 1 1. Just add 1 beat to something with 3 beats and you get 4 beats. Alternatively, what can you do? You can add 2 to something with 2 beats. So, you can take this 1 1 and add a 2, that's this, and this 2 and add a 2, and that's it, because when you remove the last number in your 4 beat thing, it will either give something with 3 beats or something with 2 beats. So, a meter with n beats, where n is now could be 100 or whatever, say a meter with 100 beats can be obtained by adding a 1 to the end of something with 99 beats or by adding a 2 to something with 98 beats. Right, so, what you are saying is that the total number of meters with n beats is the total number of meters with, so the total number of meters with 100 beats is the total number of meters with 99 beats plus the total number of meters with 98 beats. Understood? Okay, so, if I want 4, then I can take these 2 and add 2 to them, or I can take these 3 and add 1 to them. So, totally I will get 2 plus 3, which is 5. And this is nothing but the, since some of you came in late, let me show this again, this sequence. Each term in the sequence is the sum of the previous 2 terms. 3 is 2 plus 1, 5 is 3 plus 2, 8 is 5 plus 3, 13 is 8 plus 5, and so on. So, this you get the Fibonacci sequence when you look at this problem of counting the number of meters with n beats. So, here's a schematic. These blue means you are adding a 2 to something before, and the red means you are adding 1 to the end of it. So, this thing is something on which this is a network sort of, it has nodes and some of them are connected by edges. I won't go into it, but this is something that I actually do research on nowadays. So, it's related to Fibonacci numbers and Virahanka's work from the 6th century. So, what is this? I've forgotten. Okay, so guess the next number is 120, 360, 720. So, when you are looking at these sequences, one thing you can try to do is say subtract each term from the previous one, but that does not give anything nice. If you divide, however, so this divided by this is 2, this divided by this is 3, this divided by this is 4, this divided by this is 5. So, the next number should be 6. Huh? Oh, geez, I have made a 24 times 5, 120. Sorry, mistake. So, yeah, so that should be 120, and then the next one would be 720. That's what I thought. Sorry, there's a mistake here. This should be 120. So if this were 120, then these would be called the factorial numbers. So, you can be forgiven for not guessing the next term correctly. And what it is an is 1 times 2 times the product of the first n numbers. It grows very fast. If you look at what is the product of the first 100 numbers, it's this huge thing with some 150 digits or so. Okay, so this, if you just take 1 times, 2 times, 3 times, 4 times, 5, keep multiplying till 100, you get a very large number. So this thing grows very fast. So if you want a quick way to write down large numbers, you can do this. So there is a formula for saying approximately how fast it grows, and it's called, again, this name de Moivre, his Stirling approximation. So he discovered this formula, but he didn't know exactly about the square root 2 pi here, but he figured out the n times n by e to the n part, and Stirling was able to compute this thing. So this, I hope you can understand. E is this number called Euler's constant. It's like 1.7 something, 2.7 something. Sorry, 2.7 something. And so you can put this into your calculator and calculate it. So if you take for 100, this formula gives 9.3248 into 10 to the power 157. Okay, and if you look at the exact formula, this is 9.3326, and this actually has 157 digits. So they are pretty close, 3, 2 and 3, 3, so they're getting close. And this is an approximation formula for this. Okay, what are these numbers? Prime numbers. Right? So what is a prime number? A prime number is a number which has no divisors except 1 and the number itself. So is 51 a prime number? It's divisible by 3, so it's not a prime number. But 53 is a prime. How do you check if a number is a prime? Well, there's a hard way. You take all numbers that are less than it and try to divide, and if you get a remainder, then good, go on to the next number. If you don't get a remainder, then you know that it's not a prime. And as some of you pointed out, you don't have to do all numbers till 53, you can do up to square root 53, because if some number is factorized, if 53 is a times b, then one of them will be less than or equal to its square root, because the square root means a times a is that number, right? So you only need to go up to the square root. But if you ask, like here of course I didn't have an exact formula, but I have a good approximation. Here, for example, for this Fibonacci number, there is this amazing formula of de Moivre. There is an exact formula for this. And you can ask, is there a similar formula for the nth prime number? And it turns out it's a strange thing. It's something that continues to amaze me and many other people, that there is no known formula for the nth prime number. Okay, and this kind of the sequence of numbers, it's a very mysterious sequence in some sense. It's very easy to understand. Okay, number is prime or not. You can just check it. If you have a calculator, you can easily check it, or with a computer you can write a program to check it. In fact, I think again here a few years ago some Indian mathematicians became very famous for finding a fast algorithm to test if a number is a prime or not, a computer program. And this sequence has been the favorite sequence of many of the world's best mathematicians and some of the world's not so best mathematicians. So this is Euler, this is Gauss, this is Riemann, and this is our local friend Ramanujan. This auditorium is named after him, and in Madras University the maths department is named after him. So these people, I mean, so what I'm trying to say is that people have spent a lot of time thinking about this very simple sequence. There's not an exact formula, but we do understand roughly how fast this sequence grows. And this is a very old formula, more than 100 years old, It's due to this French mathematician Charles-Jean de la Vallée-Poisson. I'm probably pronouncing it all wrong. Any of you taking French here? How is it pronounced? I pronounced it right. Okay. So this guy with the long name proved this short formula that the nth prime number will be roughly n times log n. So let me give you an example. If I take this is 1 crore, I think. Okay. You start listing all the primes one after the other. When you've written 1 crore of them, you will have that 1 croreth prime will be whatever this is. This is lakhs. This is 17 crores. And if you look at this Vallée-Poisson's formula, it's like this. So this is within 90% of this. Okay, so we have some idea of how frequently prime numbers occur. Okay, it's actually even the fact that how do you know that you can always find more and more primes? So that itself is something that requires you to think mathematically. How do you know that there is no last prime number? Right? So there are proofs of that. Okay, now let's try to work on our own little counting problem. Okay, so here's my counting problem. I'll do an example. How can I break up 5 into a sum of smaller numbers? Okay, let me be more specific. I don't care whether you write 2 plus 3 or 3 plus 2. I consider these to be the same. Okay, so can you tell me some ways of writing 5 as a sum of smaller numbers? 1 plus 1 plus 1 plus 1, very good. 1 plus 4, 1 plus 2 plus 2, 1 plus 2 plus 3, no. 1 plus 2 plus 1 plus 1, which is 2 plus 1 plus 1 plus 1. So there's all these ways. I like to write them somewhat systematically. I'll start with 5 equals 5. Then I take the largest, so that's the only one where the largest part is 5. Then I try to write the one with largest part 4. If the largest part is 4, remaining has to be 1. Then largest part is 3, then that remains 2. So I can either write 2 or 1 plus 1. Then the largest part is 2, then 2 plus 3 I have already written, it's here 3 plus 2. So I have 2 plus 1, 2 plus 1. 2 plus 2 plus 1, then 2 plus 1 plus 1 plus 1. If the largest part is 1, all the parts have to be 1. So there are 7 ways of writing 5 as a sum. Right? So you can break up 5 into smaller numbers in 7 different ways. What about other numbers? For 1, there is only one way of doing it. Right? For 2, 2 ways. You can write it as 2 or 1 plus 1. 3, 2 plus 1, the 3 ways. For 4, there are 1, 2, 3, 4, 5 ways. And for 5, there are 7 ways. So what is it? 1, 2, 3, 5. So far it looks like Fibonacci, but then it becomes 7 instead of 8. What about 6? Can you tell me how many are there for 6? Can you write them all down? It's only 11 of them. Or 9 of them, or how many ever of them. So try to use this systematic way. So first you have 6. Then you have 5 plus 1. Then you have 4 plus 2. Then you have 4 plus 1 plus 1. So tell me if you've written down all the different ways. So did anyone get all the ways? $11, is it? So I'm using a computer program called Sage. I don't know if you can see the blue stuff, but I've asked for the number of partitions of 6 and it says 11. I can also ask it to list all of them. List partitions of 6 and it gives me the answer. So I hope you got all of these. 6, whoops, what did I do? 5 plus 1, 4 plus 2. So there are 11 of them, and here they are listed systematically like I was doing. This order is called, it's like, you know, in a dictionary you write words. First you start all the words which start with a, then you start all the words which start with a, and so on. And here it's sort of the reverse dictionary order. So you start with the last biggest number, which is 6. And then if you reverse this, this would be exactly dictionary order of the numbers. So this is called, mathematicians like to use big names, so we call it lexicographic order. Okay, so 6 has all these 11 things. So here's our thing. So what's the next one? How do you do that? Huh? Am I back to primes? 1 is not a prime. Good catch. So these are actually they look a lot like primes, but they are actually what are called partition numbers. So I can calculate them using my computer program here. Tell me which number do you want to know about. So 7, you would have to make a list, right? If you see what it is for 7, it turns out to be 15. So then your list keeps growing and it takes more and more time to calculate this, right? So it will get boring after a while. Maybe you could write a computer program to do it. Tell me, what number do you want to know the partitions, number of partitions of? Huh? 100? Only 100? 8? 8 is a good one. How about something bigger? 100? No, that's not big. Is that big enough? How long do you think this will take? Huh? So should I hit return, because then my computer may crash and you'll have to, oops, my finger slipped. Okay, let's try slightly smaller. Let's try slightly. This is not good. Okay, so there's this, I wanted to talk about this very interesting resource called the Online Encyclopedia of, but maybe we'll just, yeah, so there's this thing called the Online Encyclopedia of Integer Sequences. Let's try it out in real time. I hope the internet access is there. There is some problem with it. Yeah, it seems to be there. So here's the Online Encyclopedia of Integer Sequences. So you've all seen the, I don't know. So in my days it was Encyclopedia Britannica was the ultimate thing, but now I think it's Wikipedia. So so an encyclopedia is a resource where you can find out everything about everything. At least that's what it's supposed to be. So if you want to find out about the freedom struggle of Algeria, you can go to the Encyclopedia Britannica and look up Algeria, and there you'll find this. So here this is an encyclopedia of integer sequences. So you have a sequence of integers. This sometimes happens while you're doing research. You're trying to count things and you're able to count the first few of them, and then you're like, this is a very interesting thing, it's maybe somebody else has seen it before. So then you go to the website https://oeis.org, and then you enter your number. So what was our thing? 1, 2, 3, 5, 7, 11, 13. What, where were we? 7 was 15. What? 11. 11, 15, 22. Oh God, don't tell me this internet connection is not working. It's come. So it has found 86 results. But the very first one is actually what we want. The number of partitions of n, the partition numbers. So what is this encyclopedia of online encyclopedia of integer sequences? It is just a huge database. All the integer sequences that anybody has bothered to report to them is stored there, as well as a lot of information about it. So here is here there's a list of the first few. You can get a graph. Let's see. Where's it gone? No. Where's the graph? Yeah, here it is. So you see how it grows. This is up to 200. So this is 3e plus 12. So it's like right. So this is a log scale graph, and it's still growing very fast. This again has very rapid growth. We'll come back to that in a bit. There's a lot of other interesting information about this. So there are other interpretations of this number. Number of graphs on n vertices that do not contain P3 as an induced subgraph. So you need to figure out what that means, but if you don't know, then you can look at this link here. It was entered by some guy called Washington Bonfim. You can even write to him maybe, and he will help you understand it. Coincides with the sequence of numbers of nilpotent conjugacy classes in the Lie algebras GLN. I actually know what that means, but anyway, it's something. Yeah. So there are all kinds of things. Lots of different ways of thinking about these numbers. Here's an interesting one. Do you know about matrices? So the matrix of an values. So you write a0, a1, a0, a2, a1, a0, a3, a1. Its inverse is a matrix with ones and minus ones. Lots and lots and lots of information. There's actually this book by George Andrews is rather famous. This one, a very nice book. So here's you'll find even Hardy and Ramanujan's names. Here it is. Asymptotic formulas in combinatorial analysis. So the whole history of this sequence, different ways of thinking about it. And then there's some other stuff, a lot of references to articles, books, formulas. So actually this function is also a bit like, it's a bit like the nth prime. We don't really know a nice formula for computing the partitions of n. But there are something called a generating function, which maybe if I have some time I'll mention again. But let's talk about this online encyclopedia of integer sequences. This is Neil Sloan. He's a British mathematician, and when he was doing his PhD, he came across this sequence and he was trying to wonder about it, and then he started keeping on cards, recording all the sequences that he came across, and he kept them in a filing cabinet, like a library catalog, and he had all these cards and he sorted them. It's easy to sort sequences in dictionary order. So whenever somebody came up with a sequence, you would go see, is it in my thing? Oh yeah, here it is. Okay, so and so also found this sequence and has these properties. So that's how it started off. And then you can see in his hand a book. This is the first edition of the book called the Encyclopedia of Integer Sequences. And now it's become huge, and it's gone online, and it's like everything else. It's now crowdsourced. Different people contribute sequences to it. Let's watch a movie about this.
How many ways can you triangulate a regular polygon? A triangle has one way, a square has two, a pentagon has 5, and a hexagon has 14. How about for a septagon? You can try this yourself, but has someone already figured this out? You can check this by looking up the sequence in the OEIS, the Online Encyclopedia of Integer Sequences. Searching for 12514 produces over 350 sequences. We find that our polygon problem matches the Catalan numbers whose general formula is given here. There are many other interpretations of this sequence. It counts the number of paths in an n by n grid which start in the bottom left corner, only move right and up, and finish in the upper right corner. The Catalan numbers also count the number of rooted binary trees with n internal nodes where each node has 0 or 2 children. They count the number of ways for an even number of people around the table to shake hands without crossing. Lastly, for now, the Catalan numbers count the number of ways to order n pairs of open and closed parentheses. The OEIS entry for the sequence also gives formulas involving the Catalan numbers, such as sums, asymptotic growth, integrals, generating functions, and determinants of Hankel matrices whose entries are Catalan numbers. There's plenty of other information as well. This massive collection of integer sequences started over 50 years ago when Neil Sloan, a young math student, was seeking information about a particular sequence.
Back in 1964, when I was working on my thesis at Cornell, and I had a sequence. I had a lot of sequences I was trying to identify. And so I picked the simplest one to see if there was a nice formula for that. I was interested in how fast the sequence grew. So if I had a formula for the sequence, I could have just looked at its asymptotic behavior, and that was the information that I wanted. So there were various books around, combinatorics, and other books of tables, which had sequences in them, but I couldn't find a particular sequence I was interested in there. So I started writing on file patterns all the sequences that I did find, so that my next sequence, I would have a little, I would have a place to look to see. So I started making little catalog sequences, and it grew and it grew.
And grow it did. In 1973, Sloan published his first catalog containing over 2,000 sequences. The second book with over 5,000 sequences appeared in 1995. The next year, the OEIS website was launched with 10,000 sequences. As of 2015, over 250,000 sequences are in the OEIS. The site is maintained by a team of 29 editors-in-chief and over 100 associate editors. There are so many fascinating sequences. Some are well known, like sequence A5, which gives the number of divisors of n. Interesting but less known is sequence A48987, the number of possible chess games after n moves from each side. Or sequence A19473, the number of n-celled still lifes in Conway's Game of Life. And does Sloan have favorites?
Favorite sequences? Well, you know, over the years, that's changed a bit. My all-time favorite is Rackamon. Bernardo Sankoff's Rackamon sequence, A5132, which is just a wonderful sequence. In fact, it is my favorite one to listen to.
In fact, we've been listening to Rackamon's sequence during this entire video. Each sequence has its own music. Now a question for you. It concerns the EKG sequence 864413. From the description, can you figure out the next number? Give it a shot, or look it up at the 2000.
Oops, sorry.
Some are well known.
I wanted to pause it there so that you could.
Which gives the number of the top. Since EKG sequence 864413.
So if you want, you can make a note of this. An is the smallest number not already used, which shares a factor with an minus 1. Or you could look it up at home anyway. It's called the EKG sequence.
From the description, can you figure out the next number? Give it a shot, or look it up at oeis.org.
So that's just a little about the online encyclopedia of integer sequences. This kind of thing is like a complete change from how mathematics was done before. We have so much more access to information than we did. So I've used this myself, and I've also contributed to this encyclopedia, certain sequences. You can anyway, since it's kind of technical, I won't go into it. What happened to my mouse?
We count the number of ways to an even number of people around the table to shake
Let's
hands
close
without
that.
crossing. Lastly, for now, the kettle.
Okay, so he mentioned also something called generating functions. So I want to talk a little bit about that in the remaining time that I have. So we've looked at many of these sequences, like the Fibonacci sequence, the square numbers, the partition numbers. And when we looked at the OEIS entry for partition numbers, there was there's this thing called g.f. So what this refers to is a generating function. So it says product k greater than 0, 1 over 1 minus x to the k. So this is a function, but what we have is a sequence of integers. So there's a way, there are many ways, of course. You can think of the sequence itself as a function. It's a function of the integers, but here we're talking about a slightly different way. This is Herbert Wilf. He's written a book called Generating Functionology. It's a word that he made up, and it's a technology that we use to sort of play around with sequences. See, a sequence has infinitely many numbers in them, and we want to manipulate entire sequences. So one way to do this is to code them in terms of functions. Some of you have heard of Riemann's zeta function, right? That's a sort of a generating function. It's called a Dirichlet generating function. We look at a simpler generating function. The most basic generating function given a sequence is this function. So you make it a function in terms of an infinite series. So f of x is equal to a0 plus a1x plus a2x squared plus a3x squared. What is this x? Well, we won't say what this x is. It's some sort of variable. Okay, so how many of you have seen infinite series? Infinite series? Okay, it's like you know how to add a finite sum of numbers, but you can also try to add infinite sums of numbers. But let's not worry too much about it. We'll just write it like this and we'll play with it. All of you have seen polynomials? 1 plus x. So this is like a polynomial, but it's not finite. It goes on. So for example, if you take the stupidest sequence on earth, 1, 1, 1, 1, 1. What is its generating function? 1 plus x squared plus x cubed and so on. Okay. And do you know what? Have you seen this before? So this is a infinite geometric progression. If you take 1 plus half plus 1/4 plus 1/8, okay, so that sum 1 plus half is 3/4, 1 plus half plus 1/4 is 1 plus half is not 3/4, it's 1 and half. 1 plus half plus 1/4 is 1 and 3/4. 1 plus half plus 1/4 plus 1/8 is 2 minus 1 by 8. The next one is 2 minus 1 by 16. The next one is 2 minus 1 by 32. It converges to 2. It keeps increasing, but it never crosses 2, and it gets as close to, it keeps getting closer and closer to 2. So in fact, in general, if you take a number x which is between 0 and 1, strictly less than 1, then this will converge to 1 over 1 minus x. So this generating function is actually a nice algebraic expression, 1 over 1 minus x. So this is the formula for summation of an infinite geometric series. If you had a finite geometric series, it would be 1 minus x power n plus 1 over 1 minus x. But when x is less than 1, that numerator would go to 1. So here's a way to take this sequence, this stupid sequence, and you package it and you get this function. Okay, so this is the clothesline, how it looks after we hang out this sequence. Let's look at another example, 1 plus x squared. Okay, so here's a thing, we'll differentiate this function. Okay, what happens if you differentiate? This 1 has derivative 0, x has derivative 1, 2x has, x squared has derivative 2x. So we get this function. This is a slightly more interesting sequence, right? This is the sequence 1, 2, 3, 4, 5. Differentiate again, you get another interesting sequence. 2, 6, 12, 20. What are these numbers? Can you guess the next term? It's 6 times 5, 30. So it's going to be like n times n minus 1 or n times n plus 1 actually. Or something like that. So it's a product of two consecutive integers. And so this is actually 2 times a triangular number, 1, 3, 6, 10, 15. So this generating function is 2 times the generating function for triangular numbers. But there's also this n plus first triangular number. So what you get using that is that you take the second derivative, you take this f double, so this is the generating function that we have there, but then I multiply by a factor of x to account for the fact that there is a shift, and what I get is, if you just do this, you will see that, okay, so this is 2 plus 6x plus 12x plus 20x cubed. Now I multiply by x, I get 2x plus 6x squared plus 12x cubed and so on, and then I divide by 2, then I get x plus 3x squared plus 6x cubed plus 10x to the power 4. Sorry, am I scaring you here? So I'm just playing with these functions, and things are happening to the sequences that we were working with. So what we have done here is we started with the stupid generating function, we differentiated 2 times, we multiplied by x and divided by half, and we got the generating function for triangular numbers. This is the generating function for triangular numbers. Okay, it's okay, I mean you don't have to understand all the details, I'm just, but you know, if you want you can play with it later. There's a generating function for Fibonacci numbers. So this identity, right, so then the generating function is a0 plus a1x plus a2x squared and so on. Now a2 is a0 plus a1. So this will become a0 plus a1x plus a0 plus a1x squared and then we'll have so each term here, the previous two terms will occur, one with coefficient x and one with coefficient x squared, and this identity turns out to be the same as this. If you look at the coefficient of x to the power n on both sides, it's the same thing, okay, for each power of n. And so what you get is that this generating function has the property that f of x is 1 plus x squared times f of x. And if you simplify that, you get f of x is 1 over 1 minus x squared. Okay, so this kind of amazing thing you can do, you start with a sequence, you turn it into a function, and you try to play with the function to understand the sequence. The different operations on functions correspond to different things you can do with sequences: differentiation, multiplication by x, multiplication of two functions, addition of functions, taking the log. All these things have interpretations. And let's just look at how mathematicians use this. So for the partition function, there's an old so this is that crazy sequence we looked at, for which there was no sort of closed formula, the number of partitions of the integer n. There's an old formula due to Euler. It's kind of a weird formula. It's an infinite product. This looks really scary because now firstly we don't know what this x is, it's some variable, and then we are kind of taking an infinite product of such things. But don't worry, what is 1 over 1 minus x? 1 over 1 minus x is nothing but 1 plus x squared plus x cubed. And what is 1 over 1 minus x squared? That is 1 plus x squared plus x power 4 plus x power 6. What is 1 over 1 minus x cubed? So, is 1 plus x cubed plus x power 6 plus x power 9. So, you can think of it that way, and you can expand to how many ever terms you want. Suppose I want to know the first 5 terms of this. So, I will write all the factors up to x power 5, because after x power 6 and so on, I do not need to calculate the first 5 terms. So, I get 1 plus x squared plus x power 5, then this is the second factor, 1 plus x squared plus x power 4, then there are more terms, x power 6, x power 8, but I will ignore them. And here I have 1 plus x cubed plus x power 6, I will ignore that. 1 plus x 4 plus x power 8, I will ignore that, x power 10, I will ignore all. I will ignore all the terms which are of powers of x greater than 5, because I only want to calculate the first 5 terms of this sequence. So, computationally this is just like multiplying some polynomials. After x power 6 there will be no terms, there will just be 1 plus x power 6, but that I do not want, I am not. So, I just have to multiply these polynomials. And if you carry out the multiplication, which you can certainly do by hand, you will get 1 plus x plus 2x squared plus 3x cubed, and these are the partition numbers. This is how it works. And why are these generating functions so useful? This x so far is just a symbol, but what mathematicians do is they try to think of this x as a complex number, and then this becomes a function of a complex variable, and there is a well developed theory these are called analytic functions, and there are all kinds of amazing things you can do with integrals, and you can estimate the growth of a sequence if you understand this function. So, Hardy and Ramanujan used all this technology, starting with Euler's generating function, to prove that the nth term of the partition function grows like this. Okay, this is a formula that they proved. It's a paper that they published around the time of the First World War by Hardy and Ramanujan. They used a method which is it's called the circle method. Sounds very simple, but actually it's a brilliant thing, and takes some work to understand this. So, this of course I cannot, you need to learn a lot of mathematics before you can get here, but this is the kind of thing that Ramanujan was really brilliant at. many years later, Hans Rademacher improved that formula to get an exact formula for the partition function. So, this is not an exact formula in that sense. Well, this is an exact formula, but it is an infinite sum. So you can't ever finish computing this infinite sum, but you can use it to compute in practice the exact value of Pn for very large numbers n. Okay, so this is how generating functions are used in mathematics. Okay, so with this I'll stop talking. Maybe you have some questions here about these things. Any questions? Yes. Experimental mathematics. Okay. So so you know about experimental science, right? So what do? You have a question, and then you conduct experiments, and then you observe the answers, and then you come up with a theory that can make predictions which are consistent with the observations that you have. So it's experimental mathematics is similar. So what I work on is called combinatorics, and I'll show you my sequence. Right. So I was working on this problem in combinatorics is what they call the area I work in. I like to say I'm in the numbers game. So we just try to count various things, and we often end up with integer sequences. So we were working on this problem, and we ended up with a certain sequence, and we were trying to see if it's known or not, and we put in the first few terms, and we found this entry. Let's see. So this A0041 is the partition function, which we've already seen, number of partitions of n. And what we actually saw at that time on the online encyclopedia of integer sequences was this function. So we did an experiment, and we looked at this database, and we found more information about it. So this actually looked different when we were looking at it at that time. The sequence was entered by a person called Richard Stanley, and he had put in about 30 entries of it, and there was a reference here to his not here. Anyway, he has a book called Enumerative Combinatorics, and that we found some partial work that they had done towards that. So we were actually looking at this other sequence, which we found was much nicer. If you look at these numbers 1, 2, 3, 5, 4, 8, 12, 20. Okay, maybe to you they don't look very nice, but to us they look nicer in the sense that when we took their binary expansions, they were very sparse. There were lots of zeros and very few ones. So what we are doing here is really experimental mathematics, and then I wrote computer programs to compute these things. Over here you'll find the first you'll find the first 10,000 terms of the sequence, but it's very difficult to compute directly by, just like with partitions, if you want to compute it directly, listing all the partitions, it takes a very long time. Okay, so this is something similar, but we then were able to, by observing the first few, we were able to come up with a formula, and then we were able to prove it. And using that formula, we were able to compute a lot of these things. So that's a concrete example of how experimental mathematics works. And computers play a very important role in this. In the time of, I think it was I think it was Gauss who kept a list of, who was it who kept computing prime numbers in the back of his log tables? I think it was Gauss. So he would do it by hand. Every time he had some free time, he would try to write down the next prime number. And using that, he was able to. But now we don't need to do that anymore. We have amazing tools at our disposal. And now I updated these entries, and now people who come after me may be able to again find, use this to build upon our understanding of mathematics. So even though the objects are not physical objects, they are sort of mathematical objects, it's still possible to experiment on them. The one difference is that we have to give mathematical proofs of our theorems, whereas in physics, it's not possible to give a mathematical proof. You develop a theory which is mathematical, but you only see that it is consistent, it has a predictive power and so on. You cannot prove that the world will behave in a certain way. Yeah. So you saw this in the online encyclopedia of integer sequences. You can listen to a sequence. So to me, sequences are music, but maybe not to everyone else. So let's see. Will it play? Okay. So anyway, I need to. But you can think of any musical composition, you can write down the notes, and that's a sequence, right? And people do write music based on mathematical patterns. People also find mathematical patterns in classical music. So this is something you can play with if you like.
So you can calculate every next note mathematically.
Sometimes, yeah. So in like these Fibonacci numbers appear in a lot of musical compositions. It's been found. So it's not clear if, most of these musicians were doing it intuitively. Of course, Sloan, he likes to listen to that sequence, Rachman sequence. Any other questions? Okay, so if there are no more questions, we can take a break for tea.